Rates of reactions, collision theory, and factors affecting the rate of reactions. Consider this. It takes a couple of days for iron to rust, years for the weathering of rocks, and millions of years for plants buried beneath Earth's surface to be converted to coal. But when you strike a match, it burns quickly. The speed of chemical reactions can vary from extremely slow to very fast. In chemistry, the rate of a chemical reaction, or the reaction rate, is usually expressed as the change in the amount of reactant or product per unit time. This figure illustrates the progress of a typical reaction. Over time, the amount of reactant decreases, and the amount of product increases. First, let us understand the collision theory. It is used to relate the properties of particles to the rates of chemical reactions. According to collision theory, atoms, ions, and molecules can react to form products when they collide, if the particles have enough kinetic energy and at proper orientation. This means those particles that do not have enough energy to react just bounce apart unchanged when they collide. Also, the particles that are not in the proper orientation simply bounce apart unchanged when they collide. To better understand this, let's have some illustrations. Let us say, these reactants have enough kinetic energy, and are at proper orientation when they collide. What happens is an effective collision of oxygen and hydrogen molecules to produce the water molecules. Let's have another example. What if the oxygen and hydrogen molecules do not have enough kinetic energy and are too slow? What do you think will happen? This is an ineffective collision of oxygen and hydrogen molecules. This produces no reaction, and the reactants just bounce apart, unchanged. And what if these same reactants have enough energy during collision, but are not in the proper orientation? What do you think would happen? This is also an ineffective collision of oxygen and hydrogen molecules. This produces no reaction, and the reactants also just bounce apart, unchanged. Let's illustrate the previous reaction conditions, but this time, the reactants come from opposite directions. What do you think is the result? Same thing. This is still an ineffective collision of oxygen and hydrogen molecules. This produces no reaction. And the reactants still simply bounce apart, unchanged. Let's now have again the reactants with enough kinetic energy and at proper orientation. But what if they come from opposite directions? What do you think will be the result? Since both conditions are satisfied, this is an effective collision of oxygen and hydrogen molecules. The reaction proceeds, and this produces the water molecules. Let's consider another reaction. Here is the collision of nitrate and carbon monoxide molecules. Notice that the carbon monoxide is not at the proper orientation. Thus, this is an ineffective collision of nitrate and carbon monoxide molecule. This produces no reaction. And the reactants just bounce apart, unchanged. For this reaction to proceed, the reactants must not only have enough energy, they must also be at proper orientation. This is now an effective collision of nitrate and carbon monoxide molecule, which produces nitrogen dioxide and carbon dioxide molecules. The minimum energy that colliding particles must have in order to react is called the activation energy. You can think of the activation energy for a reaction as a barrier that reactants must cross before products can form. This is an illustration of the activation energy barrier that must be crossed before the reactants can be converted to products. Also, notice in these illustrations, an exothermic reaction, which releases heat, has a lower activation energy than an endothermic reaction that absorbs heat. Here are the different factors affecting reaction rates: temperature, concentration, particle size, and the use of a catalyst. Usually, raising the temperature speeds up a reaction. When particles move faster, frequency of collisions increases, which causes products to form faster. And lowering the temperature usually slows down a reaction. Having more particles into a fixed volume increases the concentration. This increases collision frequency and leads to a higher reaction rate. The total surface area of a solid or liquid reactant affects the rate of a reaction. The smaller the particle size, the greater the surface area is, for a given mass of particles. This results to an increase in the frequency of collisions, thus, the reaction rate increases. This illustration shows that making the particle size smaller results to an increase in the number of collisions, and this speeds up the rate of reaction. You can also increase the surface area of solids when you dissolve them. In a solution, particles are separated and more accessible to other reactants. Another way to increase the surface area of a solid is by grinding it into a fine powder. A catalyst is a substance that increases the rate of a reaction, without being used up during the reaction. Catalysts permit reactions to proceed along a lower energy path. The catalyzed reaction has lower activation energy barrier than that of the uncatalyzed reaction. When the barrier is lower, a greater fraction of reactants have the energy to form products within a given time. The rate of reaction of hydrogen and oxygen at room temperature is negligible. But with a small amount of platinum, Pt, as a catalyst, the reaction is rapid. The catalyst does not appear as a reactant in the chemical equation, because it is not consumed during a reaction. Instead, the catalyst is often written above the yield arrow, as in the equation above. At normal body temperature, reactions that occur in the body would be too slow without catalysts. In biological reactions, these catalysts are called enzymes. These enzymes in your digestive tract help break down the protein molecules in a few hours. An inhibitor is a substance that interferes with the action of a catalyst. Some inhibitors reacts or bonds with the catalyst, which reduces the amount of catalyst available for a reaction. This action is sometimes called poisoning the catalyst.